Alright, hey guys, it's Miss Aguilar, and I am just going over the Unit 8 review guide. I'm going to start here with the first problem of your study guide. It's not including the definitions. The definitions is the very first part of the study guide, so I'm starting with number 1, the problem number 1. Alright, so let's just get started. Label the transverse wave below with the following terms. And it's asking for the wavelength, amplitude, crest, peak, and trough. So wavelength. Wavelength is either the trough to the trough or the crest to the crest. But just don't forget that there's other ways we can measure a complete wavelength. There's one complete wavelength, and here is another complete wavelength. Alright, the next one is the amplitude. So what is amplitude? Amplitude is that vertical distance from the top of a crest to the equilibrium position, or from the equilibrium position to the bottom of the trough. And all 4 of those vertical green lines show amplitude. All right, crest / peak. I've been calling these the crest. I think that peak, I think I was just using peak last year. So anyways, let's just forget peak. I won't put peak. It's only crest. So the crest, these are the top parts of the transverse wave. And then we have the troughs, and the troughs are here at the bottom. We have 2 of them on this transverse wave. All right, longitudinal wave. Label the longitudinal wave with the following terms, and it's asking for compression, rarefaction, and wavelength. Compression. There are 2 compressions here. The compressions are just the area of a longitudinal wave where the particles are compressed together or really close together. There's a high density of particles in the compression. And then here in orange, I'm boxing out the rarefactions. Rarefactions are low density particles, or an area where the particles are in a low density area. They're spread out more, and they're pretty much back to their equilibrium position. All right, wavelength. How do we measure wavelength on a longitudinal wave? It's either a rarefaction to rarefaction or compression to compression. So there's 2 wavelengths here. Okay, state one of the relationships between 2 characteristics of a wave. Let's do frequency and wavelength. What is the relationship between frequency and wavelength? Well, we have the f, lowercase f, for frequency, and this lambda symbol for wavelength. What is the relationship? They are inversely and proportional. They're inversely proportional. What does that mean? That means that if our frequency is big, we have a large frequency, then our wavelength is going to be small. And if we have a small frequency, then our wavelengths are going to be big. That is a relationship between frequency and wavelength. Actually, let me go back real quick. We could also talk about relationships between frequency and period. What are those relationships? They're reciprocals of each other, right? So frequency is equal to the reciprocal of period, which is 1/t, and then period is equal to the reciprocal of frequency, 1/f. So frequency and period are reciprocals of each other. Oop, too many. All right, what part of a wave corresponds to the pitch of a sound and to the volume of a sound? Well, we're talking about a sound wave here. The pitch of a sound wave, or the part of a sound wave that relates to the pitch, is the frequency. So we have a larger pitch. That means we have a greater frequency, or a large frequency. The volume of the sound, well, what part does it correspond with? It is the amplitude. So the amplitude of a sound wave represents the volume. You have a large amplitude, then you're going to have a loud volume or a high volume. If you have a small amplitude, you're going to have a small volume, or the loudness is going to be quieter. What part of a wave corresponds to the brightness of a light? So this is talking about light waves. Brightness corresponds with amplitude. And the color of a light, excuse me, corresponds with frequency. So we were talking about this today when we were doing our Kahoot. If you can remember, the red end of the color spectrum is a low frequency. And the other end of that spectrum is violet. And this represents an area of large frequency. I think it's actually 860 trillion, and red is 400 trillion hertz. Sorry, I'm running out of space. All right. What is the only way to change the speed of a wave? It's to manipulate the medium. Manipulate it. Sorry, I'm sounding out my words. Manipulate or change the medium. And what do I mean by manipulate? I mean like change the characteristics of the particles, stretching out a slinky or letting it be more slack, changing the medium entirely, like moving from one material to a different type of material, like air and water. Just changing the medium, that's the only way to change the speed of a wave. And it is for a mechanical wave, not an electromagnetic wave. Don't get that confused. All right, in a uniform medium, what happens to the wavelength if frequency is increased? We just talked about that. So if we have a frequency that is large or is increased, our wavelength will, since they have an inversely proportional relationship, our wavelength will decrease. All right, if you're in an ambulance with the siren on, how will the pitch of an ambulance's siren sound to you as it moves? Well, if you're in an ambulance with the siren on, the sound's going to be constant. You're not experiencing the Doppler effect because you're moving with the sound source. But what if you're the observer and instead of being inside the ambulance, you're now on the side of the road and that ambulance is moving towards you? So here you are and we have an ambulance, let's just make it a little box, coming towards you. As it's coming towards you, the sound waves get smaller and smaller, and that means that the frequency gets larger and larger. That means you're going to have a high frequency and a small wavelength, and this means that you're going to have a large pitch and a large sound. I know that seems opposite, but when you get a smaller wavelength, your amplitude increases. So you're going to have a larger amplitude. That means your volume is going to be, or your loudness is going to be bigger. How about moving away from you while you're standing on the side of the road? So now that the ambulance has, coming towards you and now it's passing you and moving away, so it's going this way, still going the same way, but now these wavelengths or the frequency is decreasing, your wavelengths are increasing, which means your amplitude is going down. That means the loudness and the pitch are going down. They're smaller. It's not going to be as loud. The pitch is not going to be as high. That's the Doppler effect. I think a lot of you already know this is a really interesting wave phenomena. All right, how fast will light travel in air? Light in air. Well, light will travel in air, in space, in a vacuum, in water, in everything at the same rate. And it's a constant 3.0 times 10 to the power of 8 meters for every second. Remember, c is the speed of light, and it's a constant. What is that number? That is actually 300 million meters in a second. So in 1 second, there you go. Speed of light, 300 million meters. That is a crazy number, right? But that's how fast light travels every second. All right. How fast will sound travel in air and in water? All right, so sound will travel in air at a rate of 340 meters for every second. That's air. And in water, it's going to travel 1,540 meters per second in water. This is a rounded number, and this is as well. So I guess I should do this instead of that little squiggle underneath. All right, which medium will sound travel faster in, air or water? Well, we just talked about their velocities, so it's obviously water. And we've talked about this. We talked about how the reason why sound will travel faster in water is because all of the H2O molecules, and it's super dense, and you can just get sound to travel much faster. All right. Wave equation. This is our wave equation part. But I think instead of making this one long video, I'm going to stop it here and then I'll make a second part. So if you guys want to keep watching and, getting a better understanding of the rest of this, just watch the next video. All right, guys, I hope you have a great weekend.